Imagine standing on a giant bridge. Thousands of tons of steel and concrete are sitting above you. Cars and trucks are constantly moving across it. Wind is pushing against it. The temperature is changing, and sometimes the ground beneath it is shaking. Yet the bridge doesn't simply crack, collapse, or tear itself apart. In fact, some of the world's largest bridges are designed to move. They can expand, contract, flex, swing slightly in the wind, and even shift during an earthquake. So how can something that looks completely rigid actually move without breaking? The answer begins with one of the most basic problems engineers have to deal with: temperature. Imagine a massive steel bridge sitting under the hot summer sun. Steel expands when it gets hotter. Now imagine that same bridge during a freezing winter night. The steel contracts. On a small piece of metal, this change might be almost impossible to notice, but on a bridge hundreds or even thousands of meters long, even a tiny amount of expansion can create significant movement. If engineers completely locked the bridge in place, that movement would have nowhere to go. Huge forces could build up inside the structure, and eventually, something could bend, crack, or fail. So engineers deliberately give bridges room to move. One of the most important systems used for this is the expansion joint. You can often see expansion joints on roads as small gaps or metal sections between parts of a bridge. They allow the bridge deck to expand and contract without pushing the entire structure apart. The bridge can become slightly longer in hot weather and slightly shorter in cold weather, while the expansion joint absorbs the movement. But temperature isn't the only force acting on a bridge. A giant bridge also has to deal with its own enormous weight. Then there are vehicles. Every car, truck, and train adds additional load, and that load isn't always in the same place. A truck moves across the bridge, so the force moves with it. This is why engineers carefully design the way loads travel through the structure. In a suspension bridge, for example, the roadway is supported by a system of vertical cables. Those cables connect the deck to massive main cables. The main cables then transfer the forces toward enormous anchorages and towers, instead of the entire bridge carrying the weight in one simple direction. The load is distributed through a network of structural elements. This is one of the secrets behind large bridge design. The structure isn't simply strong. It is designed so that forces have controlled paths to travel through. But there's another surprising thing about bridges. They are not supposed to be completely rigid. A bridge that could never move at all would actually be more vulnerable. Wind is a perfect example. When strong wind hits a giant bridge, the structure can experience sideways forces. A long bridge can also vibrate if engineers ignored these movements. The bridge could experience dangerous oscillations, so engineers study how bridges respond to wind. They use aerodynamic shapes, flexible structural systems, dampers, and carefully designed cables and decks. The goal isn't necessarily to stop every movement. The goal is to control it. Some bridges are designed to flex slightly when wind pushes against them. That movement can actually help the structure handle the force instead of fighting against it completely. This concept becomes even more important for extremely long bridges. The longer the bridge, the more carefully engineers have to understand its movement. And one of the most fascinating systems involved is the bridge bearing. A bearing connects different structural sections while allowing controlled movement. It can allow a bridge deck to slide, rotate, or expand without transferring every movement directly into the supporting structure. Think of it like a controlled mechanical connection. The bridge remains supported, but it isn't trapped. And then there are earthquakes when the ground moves. A bridge doesn't simply experience one push. The foundations can move in different directions, the deck can shift, the supports can experience enormous forces, and if the structure is too rigid, those forces can cause serious damage. Modern earthquake-resistant bridges can use special bearings and energy dissipation systems. Some designs allow controlled movement between the deck and supports. Others use dampers that absorb part of the earthquake's energy. The idea is similar to the suspension system in a vehicle. When a car hits a bump, the suspension allows controlled movement instead of transferring the entire shock directly to the passengers. Bridge engineering uses similar principles, but on an enormous scale. Now imagine a bridge crossing a huge body of water. It has to deal with wind from different directions, temperature changes, traffic, rain, and sometimes even extreme storms. Offshore and coastal bridges face another challenge. Saltwater. Salt can accelerate corrosion in steel. That's why engineers protect important structural components with coatings, special materials, drainage systems, and regular inspection. Because designing a bridge isn't only about making it strong enough on day one. It has to remain reliable for decades. That means engineers need to understand how materials age. Steel can corrode, concrete can develop cracks, cables can experience fatigue. And millions of repeated vehicle loads can slowly affect structural components. This is called fatigue. Imagine bending a metal wire back and forth. The first few movements might do almost nothing, but repeat that process thousands or millions of times, and eventually the material can weaken. A bridge experiences a similar problem. Every vehicle crossing creates tiny changes in stress. Over many years, those repeated cycles matter. That's why modern bridges are constantly inspected. Engineers can examine cables, steel connections, concrete supports, bearings, expansion joints, and other critical components. But modern technology has made bridge monitoring even more advanced. Sensors can be installed throughout a bridge. These sensors can monitor movement, vibration, temperature, strain, and other structural conditions. Engineers can then analyze the data to understand how the bridge is behaving if a particular section starts behaving differently. It can be investigated before a serious problem develops. This is called structural health monitoring, and it is becoming increasingly important for large infrastructure. But perhaps the most interesting part of all is that engineers don't simply build a bridge and hope it survives. Before construction begins, they can create computer models of the structure. They can simulate heavy traffic, strong winds, temperature changes, earthquakes, and other extreme conditions. They can study how the bridge would respond before the real structure even exists. For especially important bridges, engineers can also perform physical tests. Scale models can be placed inside wind tunnels. Structural components can be tested under extreme loads. Materials can be tested for fatigue, and individual connections can be pushed far beyond their normal operating conditions. All of this information helps engineers understand where the limits are, because a giant bridge isn't designed around one single number. It's designed around thousands of possible conditions: normal traffic, heavy traffic, hot weather, cold weather, strong wind, rain, earthquakes, material agging, and unexpected events. The bridge has to survive all of them. And that brings us back to the question, how do giant bridges move without breaking? Because engineers don't try to eliminate movement, they design for it. Expansion joints allow the bridge to change length. Bearings allow controlled sliding and rotation. Cables distribute loads. Dampers control vibration. Flexible structural elements absorb movement. Sensors monitor the structure. And computer simulations help engineers predict how the bridge will behave. In other words, a giant bridge survives partly because it is allowed to move. What looks like weakness is actually controlled flexibility. The bridge may rise slightly in the wind. Its steel may expand under the sun. Its deck may shift during an earthquake. Its bearings may slide. Its joints may open and close, but every one of those movements can be part of the original engineering design. And that's what makes modern bridges so fascinating. They may look like enormous, motionless structures, but they are actually constantly responding to the environment around them. Every day, thousands of tons of material are moving by tiny amounts. Forces are traveling through cables and supports. Bearings are adjusting, joints are expanding and contracting, and sensors may be watching the entire system. The bridge doesn't survive by refusing to move. It survives by moving. In exactly the ways engineers designed it to. So the next time you drive across a giant bridge, look at the road beneath you. It may feel completely solid, but hidden inside that enormous structure is a carefully engineered system designed to bend, slide, expand, contract, and absorb forces. And that controlled movement is one of the reasons the bridge can keep standing for decades. if you enjoyed this engineering documentary. Subscribe for more fascinating stories about machines, structures, technology, and the engineering systems that make the modern world possible. I'll see you in the next documentary.